Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Text: The Genesis of Quantum, Unveiling Planck's Revolutionary Theory. The year 1996 stands pivotal in the annals of scientific thought, marking a period of profound transformation fueled by the revolutionary work of Max Planck, specifically his development of the quantum theory. This groundbreaking framework, the origin and development of the quantum theory, reshaped our understanding of the physical universe, leading to advancements unseen before, with implications that ripple through virtually every aspect of modern science and technology. This essay seeks to illuminate the intricacies of Planck's contribution, navigating its intellectual origins, its profound impact, and its enduring legacy within the scientific landscape. Prior to Planck's breakthrough, the scientific community grappled with the persistent shortcomings of classical physics, particularly when attempting to explain phenomena at the atomic scale. The established laws of thermodynamics and electromagnetism, despite a remarkable success in describing macroscopic events, failed to adequately address the observed behavior of matter and energy interacting at the quantum level. Scientists such as James Clerk Maxwell, with his elegant equations describing electromagnetism, and Ludwig Boltzmann, who offered pivotal insights into statistical mechanics, provided frameworks that served as a foundation, though these were inadequate to encompass the complexities soon to be revealed. For instance, the ultraviolet catastrophe, as it became known, presented an insurmountable problem. Classical physics predicted that a blackbody, an idealized object that absorbs all radiation, would emit infinite energy at shorter wavelengths, a clear contradiction to experimental observations. This disparity highlighted the inherent limitations of the prevailing understanding. Planck's work, a departure from the established norms, arose specifically from his exploration of blackbody radiation. His investigation of this problem led him to a radical proposal that energy is not emitted or absorbed continuously, but rather in discrete packets, or quanta. In effect, energy is not a smooth fluid, but rather a granular substance, composed of indivisible units. The energy of each quantum is directly proportional to its frequency, a relationship expressed by the no-famous equation EHF, where E represents energy, F represents frequency, and H is Planck's constant, a fundamental physical constant that quantifies this quantum of action. This innovative concept, a drastic leap from the classical notion of continuity, was initially met with skepticism, even by Planck himself. He viewed the quantization of energy as a mathematical trick, a means to resolve the issues in blackbody radiation, not as a representation of fundamental reality. However, the success of his formula in accurately predicting the spectral distribution of blackbody radiation, a feat that defied the prevailing theories, was undeniable. This success provided the first significant evidence for the existence of energy quanta. This groundbreaking discovery, however, was merely a seed. It needed to be nurtured and grown within the scientific community. The mechanics behind Planck's concept, which included the application of the concepts of statistical thermodynamics to electromagnetic radiation, required a significant degree of mathematical dexterity. The derivations themselves involved the manipulation of complex integrals, the application of Boltzmann's entropy equation, and a nuanced understanding of radiation and its interaction with matter. The core of Planck's approach came from linking the energy of an oscillator, the source of the radiation, not to the amplitude, as suggested by classical thinking, but to its frequency. This subtle but profound shift ultimately led to the revolutionary conclusion that energy could only be emitted or absorbed at discrete intervals. This represented an abrupt break with classical physics and was instrumental to achieving an accurate description of blackbody radiation. The immediate implications and applications of Planck's quantum theory were soon to become evident. Although initially applied to the specific problem of blackbody radiation, it quickly became apparent that this revolutionary concept had broader implications. One of the most immediate applications was in the realm of spectroscopy, the study of the interaction of matter and electromagnetic radiation. The discrete nature of energy predicted by Planck's theory provided a framework for understanding the observed line spectra of atoms, where atoms emit or absorb light at specific wavelengths. This was a phenomenon that classical physics struggled to explain. Consequently, the quantum theory provided a theoretical basis for interpreting the unique spectral fingerprints of atoms or molecules, which directly led to the refinement of our understanding of material composition. Furthermore, Planck's work served as a catalyst, spawning further breakthroughs in theoretical physics. Albert Einstein, building directly upon Planck's concept, proposed the photoelectric effect. This provided additional evidence for the quantization of energy, asserting that light itself, as well as energy, comprised packets of energy photons. Also, the contributions of Niels Bohr, who applied the quantum theory to the structure of the atom, developed a groundbreaking model where electrons could only exist in specific energy levels, thus emitting and absorbing radiation as they transition between these levels. The advancements, born of the core principles from Planck's work, transformed the understanding of atomic structure and provided a new way to interpret the behavior of matter at a subatomic level. The reception of Planck's work was not instantaneous. Initially, many scientists remained skeptical, especially those deeply entrenched in the classical view of physics. However, the accuracy of his predictions and the growing body of evidence which supported the concept of quantum gradually swayed the scientific community. Many of his contemporaries, including Einstein, recognized the profound implications of Planck's discovery, while other physicists, initially hesitant, began to embrace the potential of the new theoretical framework. The initial skepticism was due to the radical departure from classical physics, but the undeniable physical accuracy of his theory eventually won acceptance. Ultimately, the power of Planck's explanation resulted in a profound transformation. Planck, however, himself underwent a journey of intellectual transformation. He initially viewed the quantum formulation as a mathematical convenience, but as experimental data accumulated and the theoretical framework solidified, he eventually embraced the idea that energy quantization was an integral aspect of physical reality. This shift reflects the evolution of scientific understanding, where initial resistance to revolutionary new ideas often gives way to a more profound comprehension of the natural world. This conversion, itself a core element of scientific progress. Subsequent revisions and deeper understandings of quantum theory have been continually evolving, building upon the foundation that Planck laid. The development of quantum mechanics, the broader theoretical framework that emerged in the 1920s, further refined and expanded upon Planck's original ideas. Quantum mechanics offered a more complete and mathematically rigorous description of the quantum world, incorporating concepts such as wave-particle duality, the uncertainty principle, and superposition. The theory provided a deep understanding of atomic phenomena, chemical bonding, and nuclear physics, leading to practical advances in materials science, medicine, and computer technology. The influence of Planck's work radiates outwards, touching numerous individuals and preceding scientific developments. The contributions of Lord Rayleigh and James Jeans in the field of black-body radiation, for example, foreshadowed the need for a theoretical revolution to solve the ultraviolet catastrophe. Furthermore, the work of Boltzmann, the ideas of statistical thermodynamics, provided the background for many of Planck's calculations. Similarly, Planck's work directly influenced the work of Albert Einstein, who extended the quantum concept to the photoelectric effect, solidifying the idea of quantum not just for oscillators but for light itself. Einstein's work in this area shows the power of Planck's radical proposition. Also, the work of Niels Bohr, who applied quantum theory to the structure of the atom, building on the theoretical foundation provided by Planck by establishing the first working model of the atom incorporating quantum principles. Beyond the immediate scientific community, Planck's work has had a profound impact on philosophy and culture. It challenged the deterministic worldview of classical physics, opening up new possibilities for understanding the nature of reality and the role of observation. The idea of a probabilistic universe, where uncertainty is an intrinsic aspect of the physical world, transformed our understanding of causality and the nature of knowledge. The concept of the observer influenced the observed, where the act of measurement plays a fundamental role, challenged traditional notions of objectivity. Also, the very notion of the quantum, the smallest possible unit, sparked philosophical discussions about the fundamental building blocks of reality. The enduring legacy of Planck and his contributions to quantum theory lies in the transformation of science itself. He provided a critical stepping stone that revolutionized physics, giving us access to a deeper understanding of physical reality. His concepts have fueled the development of astonishing technologies, from lasers and transistors to medical imaging techniques and the information age itself. His insistence on building on experimentally verifiable evidence, while still embracing revolutionary ideas, set a benchmark for generations of physicists. Planck's legacy continues to shape the landscape of scientific inquiry, stimulating further exploration and discovery at the frontiers of knowledge. His work, a foundation upon which much of modern science is built, serves as a reminder of the ongoing journey to understand the universe in all its complexity and magnificence.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.